Well, we've seen matrices as a tool to allow us to solve a system of equations already in this class. We're going to start to work with matrices as sort of mathematical objects in their own right and use them to solve other kinds of problems. Remember that a matrix is a rectangular array of numbers. The size of the matrix we write as m by n, where m is the number of rows and n is the number of columns. So here's a 3 by 4 example of a matrix here. We're calling this matrix A. Notice that we don't have a vertical line anywhere drawn in this matrix like we might when we're using it to solve a system, right? So it's not necessarily like the augmented matrix for a system. Here we're just kind of thinking about this as its own mathematical object, this matrix. Usually we're going to call matrices by capital letters, so like capital A or B, or sometimes we'll use the letter M, right, for matrix. And if we're reading a matrix off, we would usually sort of start in the upper left and work our way across the first row and then kind of proceed. So this matrix here we would say is the matrix 1, 2, 0, 3, -1, 4, 5, 2, 2, 0, 1, -3. We can also think of matrices as ordered collections of vectors. So again, same 3 by 4 matrix here. We could write this as a matrix where we consider each of these columns as vectors in R3. So we might have A written as sort of the matrix consisting of the vectors v1, v2, v3, and v4, where v1, v2, v3, and v4 are each of those columns. So v1 is the first column, 1, -1, 2, v2 is the second column, so on and so forth. In this case, a 3 by 4 matrix is an ordered collection of 4 vectors that are all elements of R3. Thinking of matrices as collections of vectors allows us to think about a way to use scalar multiplication with matrices as well as addition. So we're going to kind of carry over the way we were using scalar multiplication and addition from vectors. So for scalar multiplication, if we've got scalar C times a matrix whose columns consist of the vectors v1 through vn, then the result will be a matrix with the same number of columns, still n columns, where each column is now just the scalar multiple of each of those column vectors. So CV1 becomes the first column, CV2 the second, and so on and so forth. And then if we want to add together two matrices, now these two matrices we're adding need to be the exact same size. So in this case, they both have n columns, and each of those n columns would be vectors in the same space, let's say Rm potentially. And so we have the sum of these two matrices whose columns are u1, u2 through un, and v1, v2 through vn. The result would just be what we get if we were to add each column as sort of vectors. So u1 plus v1 becomes the first column of that sum, u2 plus v2 the second, all the way up to un plus vn. So let's take a look at an example. You can see we've got these two matrices here, A and B. We're going to consider their sum, A plus B. So we want to maybe write this out. So A, 1, 2, 3, 4, plus matrix B, 5, -1, 2, 0. And the result will be a 2 by 2 matrix. These are each 2 by 2 matrices, so we can add them together. They're the exact same size. And the result will be the 2 by 2 matrix we get by just adding together each column as if we were adding vectors. This really boils down to just adding together these matrices kind of component-wise. So we'd, in this top left, get 1 plus 5, and then 2 plus -1, and then 3 plus 2, and then finally 4 plus 0. And so the final result here would be the matrix 6, 1, 5, 4. If we move on to scalar multiplication, we want to take this 2 by 3 matrix A here and multiply it by 3. So 3 times 1, -2, 0, 3, 4, 5. Again, we're borrowing sort of our scalar multiplication of vectors and doing that column by column. This will similarly kind of boil down to just essentially multiplying each component by that scalar. So the result will be a 2 by 3 matrix, which we get when we multiply each of those components by 3. So 3 times 1, 3 times -2, 3 times 0, 3 times 3, 3 times 4, and 3 times 5. And then the final result will be matrix 3, -6, 0, 9, 12, 15. So fairly straightforward there. The other operation we're going to define here is matrix vector multiplication, and we're going to see a wide range of applications of matrix vector multiplication as we move through this course. So the product of a matrix A by a vector X is the linear combination of the columns of A using the components of X as weights. So if we have a matrix whose columns are the vectors v1, v2 up through vn, and X is the n-dimensional vector with components C1, C2 through Cn, then AX is going to be the vector C1v1 plus C2v2 plus all the way up through CNVN. So we defined this concept of linear combinations in an earlier video, and so we're taking advantage of that here. So let's see an example of that. I would just to make a note here, if A is an M by N matrix, then A times X is only defined when X is an n-dimensional vector, and the product AX will be an m-dimensional vector. So important there that this is only going to be defined in certain scenarios. So let's try this example here. So we have a 3 by 4 matrix. So maybe I'll just write that up here. So a 3 by 4 matrix, and this is a 4-dimensional vector. This is in R4, so that is good. So our matrix vector multiplication A times X is going to be defined. And so AX in this case will be equal to the vector we would get by taking each component of X and multiplying it by each of the columns of A. So the result will be a vector in R3. And so let's just write that out. It's going to be 2, which is we're getting from this 2 up here, times the first column, 1, 3, 0, and then plus -1, I'll just write minus the second column, 2, -1, 5, and then plus 3 times 0, 4, 1, and then finally plus 1 times -1, 2, 3. And so now we can just put all this together. And we'll do this in a couple of steps here. So first, let's multiply each vector. So we get 2, 6, 0, and then plus, I'll just put that minus in there. So -2, 1, -5, and then plus 0, 12, 3, and then finally plus our -1, 2, 3. So the result is, again, a vector in R3. 2 plus -2 is 0, plus 0 plus -1. I guess we get a -1 there. And then 6 plus 1 is 7, plus 12 is 19, plus 2 is 21. And then 0 minus 5 plus 3 is going to be -5 plus 6, so 1. So that is our result here. Maybe seems a little bit strange to define matrix vector multiplication in this way. Might be a little bit strange to think about defining matrix vector multiplication at all. Why would we ever need to do this? We are going to pretty quickly here, hopefully, convince you that this is something that is worth doing, multiplying a matrix by a vector, and also why this particular definition actually makes a lot of sense. Last thing we want to look at here is proposition 223 on the linearity of matrix multiplication. So a few things here. If A is a matrix, V and W are vectors of the appropriate dimensions, and C is a scalar, then first of all, A times the zero vector equals the zero vector. Just a note that these two zero vectors might be slightly different zero vectors, right? They might live in different dimensions. So one could be in R3 and the other in R2 or whatever, but they are both just the vectors consisting of all zeros. So just as a reminder there, this zero vector is just, whatever size it needs to be, the vector of all zeros. Second here, A times the scalar multiple of a vector v by c, so A times the vector cv is equal to c times the vector av. So sort of this idea that scalar multiplication can move in and out of matrix vector multiplication. And then we have this third property here that A times the sum V plus W is AV plus AW. So we can sort of distribute matrix multiplication into these sums of vectors. You could see sort of one of the things we're trying to do here is demonstrate how matrix vector multiplication works with the other operations we've already defined on vectors, namely scalar multiplication and addition. And technically, we'd want to prove each of these, right? This is a proposition, so this does require some sort of formal proof. I'm not going to go through the proof here, but you could certainly try some examples to maybe convince yourself that this is true, and then maybe even attempt to formally prove these. Really, the way you would go about that is just by kind of setting up some general vectors, some general matrices, and using your definitions of matrix vector multiplication and scalar multiplication of vectors and addition of vectors, and everything should just sort of work out nicely.